Hello everyone. In the last video, we were looking into the concept of data slew check. This is again another kind of timing check. So we send the input waveform from the input port of the chip and allow it to propagate through the complete logic. And at each and every tap point of this particular logic, we check for the transition value, and that transition value should be greater than 20 picosecond and less than 400 picosecond. Now, why do we even arrive to this particular transition limits? Let's try to look into that. So there are multiple reasons. There are reasons of power, there are reasons of performance. So let's look into the reason from a power point of view. Okay, what we'll do, we'll feed this particular input waveform to a CMOS logic. And why CMOS logic? Because CMOS logic is the one that is being used to make the most of the logic gates. And there are reasons for it, because when your PMOS is turned on, your NMOS gets turned off, and vice versa. And because of that, there is a lot of power saving. So we'll talk about why we use CMOS logic in a separate section. Let's try to understand what happens when we feed this particular waveform to a CMOS logic. So during this portion of your waveform, this is the logic 0 portion of your waveform, your PMOS is on. Okay, during the logic 1 portion of your waveform, your NMOS is on and PMOS is off. But what happens during this transition value? So during this transition value, your PMOS is getting turned off, your NMOS is getting turned on, and there is an area, there is a portion of the waveform during which both PMOS and NMOS are turned on. Okay, so this results to a flow of current, a flow of short circuit current from the supply to the ground. Okay, so basically whenever there is a flow of current, there is amount of power that gets dissipated. So power, there are three categories of power. One is leakage power. Leakage power is the one when both our PMOS and NMOS are turned off or turned on, or at basically static or at a static condition. Okay, there's a short circuit power, which is what we are explaining now, and there is a switching power, which will be covering in a separate section. Okay, so we are looking into this particular values of transition from a short circuit power point of view. So when you during this particular portion, your supply and ground are short circuited, and as a result of that, there is a power dissipation. There is a short circuit current that flows from supply to ground, and there is power dissipation. And larger the value of this particular transition, more the amount of short circuit current that flows from VDD to ground, and there is very huge loss of power. And imagine the amount of transitions that the circuit might have. If there are huge number of transition and the transition values are even huge, greater than 400 picosecond, then the amount of then just imagine the amount of power loss that can happen. Okay, and we're talking about millions of transistors on a chip, on a single chip. Let's try to get even more deeper into this concept. So what we'll do, we'll take a real scenario where our output is connected to an output load capacitance. Okay, assuming that this is driving some logic out of it, and we'll just derive the capacitance, the load capacitance. We'll assume some value for load capacitance. Okay, let's take the extreme conditions over here. Let's say the output load capacitance is very high. Okay, if the output load capacitance is very high, you see there is a tap point over here. So according to your Kirchhoff's law, the current that flows into this CMOS, into this NMOS logic, is the addition of this current plus this current. Okay, there will be a current which is flowing from here, and there will be current, a short circuit current which will be flowing from here during this area. And in this case, whenever your CL or the output load capacitance is very high, the amount of current that flows through the discharge due to the discharging of this capacitance, that is very high compared to the short circuit current. So short circuit current is very minimal, and this is a very good technique to reduce your short circuit current to some extent. And we'll try to explain what are the disadvantages of having the high load capacitance. But at this point of time, you have this particular tap point where you have this particular common point where you have two sources of current, out of which one source of current is very high, and as a result of that, you get rid of the short circuit current. So out of the three kinds of powers, which is one is the leakage, the other one is the short circuit power, and the other one is the switching power, you get rid of one of the power by using this particular technique. So there is only switching power which is present over here, but there is a catch over here. Since you now have a very high output load capacitance, the output transition waveform will look something like this. It will take a long amount of time to get discharged, and this particular waveform will be fed to the corresponding logic. Let's say it is going to be fed to another inverter. So for this particular logic, because of this huge transition, you see a huge amount of short circuit current for this particular inverter. Okay, so output load capacitance should be again within certain limits, and one way to measure the output load capacitance is to measure the transition value. So if the output transition at this point, or let's say the transition of this particular waveform is less than 400 picosecond, we are in certain limits. Okay, this is a very good technique to reduce the short circuit power, but it should not be used very extensively because of reasons that the next stage will get affected. Okay, now let's look into a different case where your output load capacitance is very low. Okay, so this is what I just explained, that during this area the next stage will have a huge amount of short circuit current. Okay, so let's look into a case where your output load capacitance is very low. In that case, the amount of current now again there are at this particular point of time there are two sources of current, which is short circuit current, this one, and the current from the discharging current from this load capacitance. Now since the load capacitance is very low, it will get discharged very fast, so the discharging current will be very fast or will be very low compared to the short circuit current. And the short circuit current is the maximum current. The maximum current will be short circuit current. So we should be avoiding having a very low transition. That's why we have set a value of output. The output transition should be at least greater than 20 picosecond. If it goes less than 20 picosecond, the short circuit current will be maximum. If it is exactly 20 picosecond or somewhere in the range of 20 picosecond to 100 picosecond, there will be an amount of short circuit current which will be significant compared to if the output load capacitance lies somewhere between the where we see a transition value, let's say less than 400 picosecond and greater than 100 picosecond. So there will be an amount of short circuit current. This can't be completely avoided, but we can actually reduce it by optimizing the output load capacitance. There is a way to reduce it. Okay, so this is one of the reasons that sets the limits for our output transition, for our data transition. So this is where your limits come from, your data transition. There is a lot of characterization that happens for even achieving to for even reaching to these values 20 picosecond and 400 picosecond, and after the lot of characterization that we do, we come up with these values, and the data transition should be within this particular limits. That is one of the reasons of having a data transition in this limits. There are other reasons also. For example, there is another reason where, let's say, this inverter as a logic was characterized between this range of transitions, and if the value of this particular transition exceeds 400 picoseconds or it is less than 20 picosecond, the circuit doesn't behave as it is expected to behave. So what these values tell us, that if the data transition is within this limits, the circuit will behave as we want it to behave. Okay, so these were the primary reasons, and we'll talk a lot about the power, the transition values, and we have already spoken about them in a separate section of videos in the clock tree synthesis videos. You might want to have a look into those videos. We have talked about all kinds of power over there. Okay, so since we have understood the data transition values, so across each and every tap points we pick up the data transition values, we check them against these values, and this check happens at a placement stage itself, so that we don't miss anything. Okay, so at least we have placed sufficient amount of buffers so that at this stage we don't see any transition violations. Okay, so we check it for this yellow logic, we check it for blue logic, and we check it for the green logic, and we understand completely that the data transition lies in these limits, and then we proceed forward. If there is any path in which the data transition exceeds 400 picosecond, or it's below 20 picosecond, we do some surgical changes into the circuit. For example, let's say we after the analysis we understand the path from D4 to buffer has got an input transition which is greater than 400 picosecond. We add some extra buffers to it, or we do something. Okay, so it's very good to understand the data slew value at a placement stage itself, so that we don't see any surprises in the further stages. Okay, so with that said, we'll move on to the next topic, which is the clock tree synthesis topic. So we will be briefly talking about the clock tree synthesis, as the complete clock tree synthesis has been explained in a separate set of videos. Let's try to briefly talk about clock tree synthesis in the next video. Thank you.